Oh, wow. That was abrupt. Sorry about that, guys. Hello again. I am back on the stage, but I promise to not be staying around for too long. I am actually just here to introduce our next speaker. Our next speaker is, in fact, an instructor and researcher at securinghardware.com, specializing in silicon debug, security validation, and hardware penetration testing. This is pretty cool. For over a decade, he's trained hundreds worldwide and developed tools, courses, and playful hardware hacks for conferences and the NSA playset. So, if y'all would be ever so kind, please welcome to the Hackaday Super Conference stage, Joe Fitzpatrick.
Thank you, Allie. How's everyone doing? It's kind of neat to be here because normally I'm the hardware guy at the security conference, and now I'm the security guy at the hardware conference. And like, I feel bad because like I go and pretend that I'm a hardware hacker in front of all these security people, and then I see all the crazy stuff happening out there, and like, oh, I wish I could do that stuff. But I do have some stupid tricks. There we go. Yay, there we go. Full screen. Yay. So we're going to probe pins for protocol polyglots. Does anybody know what a polyglot is? So polyglot is like two things that's the same, two different things that look like the same thing. So it came into use with like PDF files that were also zip files. So you can open up in a PDF viewer, you can open up a zip file viewer, or you can open up in a Nintendo emulator, and it would work as different things in each of those things. So I've been kind of thinking about that with respect to hardware protocols. A little bit about me. I like to dress up as memes for various reasons. I do have my own set of conspiracy theories we can talk about another time. But yeah, I teach classes on hardware hacking for software people and security people who just trust the hardware for some reason. But hopefully that's changing over time. Who remembers this, the silly add-on original spec? This is years and years and years ago. It was just a tweet, and it left a few details undefined, so I took advantage of that, right? Like it says VCC is 3.3 volts. It doesn't say which way it goes, right? I put together, whoops, I think I skipped one there. No, there we go. So I put together a micro badge, this little tiny badge. You'll notice it's missing a battery. That's because the power is supposed to come from the add-on, right? Whatever. I thought it was pretty cool. Really tiny badge. I had a bunch of them at DEF CON. I was handing out these little add-on arms and stuff and faces so you could build yourself a badge. But you can see there's not much there. It's just this tiny little itty-bitty thing. It was an AT-Tiny 85, if you're curious. And then I wanted to make some add-ons, but I was too lazy to put another microcontroller on the add-on to receive the I2C and go and turn it into a pattern for flashing lights. I2C is a pretty simple protocol, right? You have what's called a start condition, where your your data line goes down, and then your clock line goes down. That says, hey, devices on the bus, listen, right? And then stuff happens. We don't care about that. But at the very end, your clock line goes down and your data line goes up, right? And that's, hey, devices, you're off the hook, you're done. Go back to your regular business. Wait till you hear another start condition. And that's when the party starts, right? So who's seen this protocol, WS2812 protocol, right? This is these neopixels, right? You basically have 8 bits of red, green, and blue that shift through and give you a 24-bit color on one LED, and then it passes everything on to the next LED, and so on and so forth. But you have to do it at 400 or 800 kilohertz, depending on the specific manufacturer of the silicon you've got. You have to have this clock in between. They have to either be a 1 or a 0, but you always have this return to 0 code. You end up at 0 every time. And so I could do this on one of those wires between the stop and the next start condition, and it wouldn't violate any of the I2C rules, and it was great. And the other thing that was kind of cool is that this thing, it needs this clock. It also says if nothing happens for a while, it's a reset condition. We ignore everything. And if we don't have 24 bits in a row, you probably weren't meaning to talk to us anyway, so we'll ignore it, which is great. So we have I2C is undefined X and don't care outside those conditions. We'll flash those LEDs. We call it good. So anything goes on either line all by itself. You just don't want it to do both lines at the same time. And even between the start and stop conditions, anything goes on SDA. So if we look back, come on, slow. If we look back at this protocol, right, oops, that's the wrong one. There we go. If we look back at this protocol, the only time anything matters, eraser, is when this clock rises, right? When the clock rises, it checks the value of the data line, and it assumes that that's what it is. Beside a setup and hold time, like after the clock has been gone high, when it's high, you do whatever you want, right? It's kind of a free for all. So you have a lot of overlap of don't care conditions where you can put two protocols onto the same wire. So basically what you want to do is you want to look for this forgotten bandwidth. You've got protocols. You have protocols that define what has to happen when and where. And they also say what doesn't have to happen and what is don't care and what doesn't matter. Sometimes it's undefined. Sometimes it's user-supplied or user-defined values that you can plug in and don't matter. Like if you have a 12-bit ADC and it takes 2 bytes, right? You've got 4 bits that don't matter there. You could probably use that for something else. Also, what makes it invalid, right? If you have a protocol you're speaking and you're receiving packets, how do you know if the data is good or bad? Anybody? Checksum, right? A checksum, parity bits, stuff like that. So if you intentionally give a bad checksum or intentionally give a bad parity bit, what do you do with that packet? You drop it, you ignore it. Some fancier protocols you might request to resend it, but for the easy ones, we just ignore it. Which again, turns that whole bunch of data into don't cares, which means I care. So yeah, what makes it malformed versus correct, right? Oh, this is really small, I'm sorry. What happens to those malformed packets? Hopefully they're just dropped. So let's look through a couple protocols and see where we can find places where we can cram our polyglots. Okay, first we've got I2C. I already mentioned it, right? Between our stop condition and our start condition, all this area we can do whatever we want. We can have it on one line or the other, just not both at the same time, because we risk the we enter the risk of having an accidental start or stop condition. Again, we have the rising edge that matters, but everything else, while it's high, doesn't really matter. Once we've captured that bit, the device on the other knows what it's supposed to be. We can do whatever we want. Yeah, I explain it on the diagram, and then I have a slide that explains it. So the WS2812, the two things before, right? If it's less than 20 bits, it's probably ignored, and we need to have this 400 or 800 kilohertz clock edge that every single bit has a clock edge because it's a return to 0. It starts at 1, it returns to 0. You have 24 of those in a row. Those are 24 bits. We got it. We're good. If we happen to send a byte over UART, that could be anywhere from 3 to 5 transitions, right? It'll ignore it because it's not enough data to actually trigger anything. Also, your UART is probably going to be a lot slower than the 400 kilohertz that it wants. So let's talk about UART, right? UART also has these framing bits. It has a start bit and a stop bit. What happens if your stop bit isn't the right value? Anybody? Call it out. Error, framing error, right? That's what PulseView calls it when you use a logic analyzer to look at it. Basically, if you're using a serial adapter and you're looking at a text stream, if it gets a packet with a framing error, with a stop bit that doesn't line up, it'll assume it was noise and ignore it and drop it. You'll never even see it on the console, which is great if we want to use that for other stuff. The other thing we can realize is that basically we have a start bit, right? We think of the start bit as being this whole thing, but really what matters is the falling edge of TX. Now, if we were doing RS-232 and it was 0, negative 15 and positive 15 volts, it'd be inverted. But we're talking about TTL UART, so we go from 5 or 3.3 volts down to 0. That's the start bit. That's when we trigger everything that's going to happen. And we're going to sit here and wait not 1, but probably more like 1.5 baud rates, right, until we get the middle of our next bit of data, and that's where we'll sample. That's where we'll sample, right? So every time we have a UART, we actually have this window of opportunity to put whatever the heck we want on the bus, right? So why don't we? And yeah, so framing error, wait, and then we can do a start bit. We can also do 8 bits of don't care, and then a bad stop bit, and we have a bunch of don't care. Oh, it gets more complicated. Now we have more wires. So SPI is designed to actually cram multiple devices in the same bus by just sharing the other wires, but then having the chip select signal be separate for each device. So you can have 8 SPI devices, each with their own chip select signal, and you can use it. You can share all the other signals, which is great. You can also use that chip select signal when it's not being used for something else, if you don't start toggling the clock at the same time, right? Because what happens? SPI, you start the transaction, right? You select the chip, and then you start ticking the clock. But this window right here, right? Fair game. You can do whatever you want. This window right here, no rules. Do whatever you want. You do have to be careful because, right, you have the wire that goes from your controller to your device, right, that you control, and then you have a response from the device back, which the device controls. Except when your chip select goes high, what are you supposed to do as a device? Tri-state. Get off the bus. Let it be. It's someone else's bus. And if it's someone else's bus, it might as well be my bus, right? So yeah, again, nothing happens when CS is high. Every pin, every other pin, whoops, is now a don't care, even peripheral out, controller in. So depending on the type, only the rising clock edges matter as well. There are different styles of SPI where sometimes they use the falling edge for the receiving, whatever. But yeah, if you pause the clock, you've also paused everything else, so you can do everything. Just be careful of POCI, because that's still going to be active in that time. Who's played with USB? USB gets complicated because it is a differential signal, sort of. It's a fake differential signal, really. It's two digital signals that happen to be opposite of each other. And we're just looking at low speed and full speed USB. But basically, you can see we have one signal that does one thing, and the other signal does the opposite. And then at the end, we have like an end of packet, which is what they call single-ended zeros, right? We treat it as, instead of differential signal, as a single-ended signal. And the single-ended zeros both being 0, that says, oh, that's the end of our packet, we're done. What does it have, though? It has this great little CRC. So number one, if we don't do the whole differential thing, right, we don't have any transitions, it's going to be fine, right? If we mess up the CRC and give a bad CRC, it's also fine. You do have to be careful, though, because the end of packet is single-ended zeros, both zeros on both lines. But there's also a reset condition, where if you have single-ended zeros on both lines for too long, it resets the connection, which causes more traffic, which is a bad thing. So differential signals, don't worry, it's not that bad. CRC is don't care. I should come up with an alternate backronym for CRC that means I don't care. Any ideas? No. And be careful of that single-ended zero reset. So I don't know if I'm going way too fast or way too slow. Is everybody learning something? Yes. OK, good. Is this a stupid trick? Yes. OK, good. That's my goal. This is a stupid trick. Don't do this in production. Do this for fun. So let's get fancy. That's a nice clock there. You mind if I use it as UART? So we're looking at SPI. You see SPI. And this is not the most beautiful capture, because some of you might be critical of the fact that I only have one high and one low sample. I should be using a higher sample rate. But I just grabbed a screenshot, so don't worry about that. But we have a clock, and we have this assumption that clock rates just go up and down and up and down and up and down, right, in a somewhat regular fashion. Is there any requirement in SPI that says it has to do that? Nope. Is there any requirement in I2C that it says it has to do that? No. People think I2C is supposed to go at a couple certain speeds, but actually they just have to go at least that speed. They can go much slower. The clock is whatever the master or the controller wants it to be. So if we actually used UART for our clock, right, we could transmit a UART data that would be completely valid, and just make sure that we transmit our data at the same time. I don't have a timing diagram or an example of that. I apologize. But no problem. No reason why it shouldn't work. Sounds like fun, right? So, SPI, right? And then there's UART hiding in my SPI. But there's also SPI hiding in the UART, right? And really, both of those are the same thing. So that's yeah. So anyway, what if your UART had its own UARTs? Right? So I said before, you've got 1.5 times the baud rate for one bit between your start bit and your first bit, that you can do whatever you want, and no one's going to mess with you. I mean, yeah. So let's not go to waste. So here's UART, right? We said before, we've got our start bit, or more importantly, our start trigger, right? And we're going to spit out the letter C. So we've got 1, 1, 0, 0, 0, 1, 1, 0, and our stop bit. That all looks good, right? Now, if we wanted to throw some extra bits in there, that's fine too. So here we've got a C, but here we got a framing error, right? Because what happened is I spit out some bits, and then I did a bad stop bit, right? So this is going to get thrown out. And this is also, start bit, some junk data, and then a stop bit, and a framing error. PulseView also throws in this break condition. Basically, if you do nothing on a UART, keep it low for a certain amount of time, it's essentially a break. It's like close the connection. Not many things actually honor that anymore, but you may have some trouble with it. But what if we put 2 UARTs on one pin, right? So we've got one pin right here, and I've got 2 protocol decoders right here on that UART pin. We've got our C spitting out right here, valid UART, right? And then we have some garbage out here that's all framing errors. But if we look down here, here's our start bit for our next protocol. We've got 0, 0, 1, 0, 0, 1, 1, 0, and a stop bit. It's totally valid. It parses properly. But you look what you have up here. It doesn't look anything like the same thing. So pretty cool, huh? If you plug this in and you look at it at, I think it's 115, 115.200, right? You'll get this. You'll see a C and nothing else. If you go and plug it in, I think I did 16x, so it's what, 7,000 baud, right? You'll get a D. So I don't know what the real use of this is. It's not something you want to do in production, but like if you do want to like actually like if you're trying to like covertly transmit some messages, like exfiltrate data, maybe this is a good way to do it. So a bit about how to do that. Time 3:46, so I still have 4 minutes. I don't know if does that include questions or not. I don't know. Any questions? Okay. So how do we do it? I just used Arduino. The reason was because I was using Atmega 32U4 because I know the instruction lengths of all the procedure calls and everything, so it's really easy to do that. When you use something like CircuitPython or using other microcontrollers that have other processes running, you have to use like DMA and all the complicated stuff, and that's too much work. This is just a stupid trick. So do bit, right? We're going to write a value, and we're going to delay a certain microseconds. That's easy. So let's do UART. To do byte, we do our start bit, and then we shifted our 8 bits, and then we do our stop bit, right? Now, we also want to be able to do that bad byte, right? We want to do a bit that doesn't actually transmit as anything. So what we'll do is we'll do a start bit, and then we'll spit the data out again, but then we'll spit out a 0 for a stop bit, an invalid stop bit. It'll get like rejected, and then we'll go back to the 1 that it should be, so like it's clean afterwards, right? Now we hide those bytes into bigger bits, so we're going to bitbang again. So we'll do our bad byte with value 1, length 1, and then we'll do a bit that's value 2, but we're going to do length 2 minus length 1 minus 10. Why 10? Because we have 8 bits, start bit and stop bit, so 10 times that length. I'm sure there's a 0, divide by 0 error here somewhere that I have to figure out, but I'm not going to do that right now. Well, actually, no multiplication. I multiplied, not divide. Anyway, so yeah, you have to make sure you pause long enough to get the second baud rate that you're doing. And then we can do the same thing without the hidden byte. What we do is we do a bad byte first, a byte that doesn't get received, and then follow it by a space for the rest of that good byte. And then, of course, you have your loop to do the 8 times of the actual top-level byte, which calls the bytes for the other ones, and so on and so forth. And here we go. We're going to write hidden bytes. We're going to write a C, and we're going to write a D. And we're going to do our baud rate, and our baud rate times 16. And then we'll wait 100 seconds. And that's how we got that stupid diagram that I showed you a minute ago, which is, two UARTs, 1 pin. Cool. Fun? Now, so what? Did anybody learn something? Yes. OK. Is anybody going to go use this at work? Yes. Is anybody going to go use this for fun? It may be a good capture the flag exercise to hide data. The point is protocols hide more data than they appear to contain. That's a long sentence, really skinny. And next. So following the rules is as much about knowing the rules as knowing when you don't have to follow the rules. Now, I wish some people in this country wouldn't take that so far, but we should all kind of think about that when we deal with electronics. Again, do this at home, because this is a fun project just to get you to understand the protocols at the lower levels, how they're actually working, what's actually showing up on the wire. Don't do this at work because stuff doesn't work, and then you might get in trouble. If you want, I can flip over perhaps to the Windows key Shift 0. Maybe not. Oh, wrong screen. Window key Shift 0. Oh, come on. Maybe I should just go for questions. Questions?
How frequently have you done this at work?
I mean, I'm working right now, so as a independent entrepreneur and self-employed, all of my polyglots have been for work. That way, they're tax deductible. Speaking of hacking, any questions? No? Yeah. Well, so it was that first, the very first silly add-on standard, right? And it was as much because it was a silly standard and it was incomplete, and I wanted to take advantage of all the deficiencies in the standard as opposed to actually complying with it non-maliciously. Hence the badge that didn't have a battery, right? And the add-ons that were just LEDs and not actually receiving I2C. So, but I was compliant. I was totally compliant with the spec. It was only 3.3 on that voltage line, and it was only valid I2C on the two I2C lines. So malicious compliance. So another thing you should all practice is malicious compliance. It's very helpful sometimes. Yeah? Have I done anything with the USB? Not successfully. So one of the issues is bitbanged USB is crap. And so you get it to work, and that's a miracle. And getting it to not work is really easy. Yeah, I have messed with it, and I have gotten extra stuff in there, but it crashes your USB stack often enough when I tried it. And this is 8 years ago, so I've been fiddling this for a long time, and finally decided to talk about it because I never actually did anything productive with it, and so might as well. So maybe there's some room there. USB stacks have gotten a lot more robust in the past 8 years, thanks to tools like the face dancer, which lets you go and be a malicious USB device. So maybe that's more reliable now than it used to be. Yeah? Can you fit more than two UARTs in the same pin? It depends how fast you're comfortable doing UART, right? Because I found it easy to do when I had like 16x speed difference between the two. So I could theoretically do a slower one, 1/16 of 7 kilohertz, and a faster one and a faster one. Getting the right baud rates would probably be helpful because that lines up. Most UARTs will go to 115K bit per second. The FTDIs will go, I believe, to 4 megabit per second. And some of the higher end ones, you can get like 32 megabit per second UART, but I don't trust that, and I'm not sure you could actually cram much in there reliably. So, and certainly not over long wires. Yeah?
Do you have any difficulties at the physical layer, like matching pieces or multiple numbers or things like that?
If I did, I didn't notice. So the question is, are there any electrical physical layer issues like impedance matching? And I didn't notice because I didn't pay attention because it just worked. I2C, you've got a pull-up that gives you the high voltage as opposed to having to drive it high. So you do have to be sensitive to that because you can't go outside of a certain speed range because your pull-up is only going to pull your 0 to 1 fast at a certain speed. You don't want to go too fast or too slow. Yeah? If you buy cheap hardware from China, it's the fastest way to detect something like this, logic analyzer on the data pins. But again, you have to know what you're looking for. I have a slide that I often use in my classes where we look at the SPI flash chip being read from a MediaTek router. And what's neat about this is the MediaTek router has a couple, so it shows a clock signal, which, too many screens in front of me. It shows a clock signal for SPI. But the clock signal looks like this. It's just like this. It has that gap between some of the clock signals. Like, why is that there? And it actually is on the MediaTek chip. It's like half a clock cycle extra in there. And what it is when the MediaTek chip is driving SPI and sending out the address, it sends out 8 bits, and then it pauses for half a clock and sends out 8 bits and sends out 8 bits and sends out 8 bits. But then it goes into receive mode, and it just clocks it continuously. So you can just look at that timing diagram and look at the clock and realize that when the clock has a slight glitch in it, when it's like an extra space between every 8 bits, it's the CPU talking on the SPI. And when it's continuous, it's the CPU asking for data on the SPI. So weird protocol quirks like that I liken it to the dialect of the protocol. It's not the actual language, but it's, you can tell what someone's talking about when you kind of read into the intonation, if you know what I mean. Everybody good? Any questions? Who's going to do something stupid after this? Good, thank you.